Welcome to week 4 of Haskell and Coffee. We are dealing with filters, maps, and modules today. We've mentioned maps briefly. We talked to we uttered the name maps before, and we've talked a little tiny bit about modules because even though we didn't know what they were, we've been using them. One thing about using things that you don't know about is it leads to potential problems. So we have to know about modules, and so we will talk about those as well. And so hopefully you have coffee, or maybe not have coffee, and have some chamomile tea or something. So we've already talked about coffee, so I'm just going to keep going for today. So from last week, we were talking about palindromes, and we had the condition where empty strings are not really a palindrome. They're just an empty string, and so we dealt with maybe. Now we're going to equip you. So we dealt with the strings not being, empty strings not being a string with the maybe. We entertained, an empty string is just maybe not a string. It's nothing. And now we have these other conditions. Strings with capital letters don't get recognized as palindromes. Strings with spaces aren't captured. Things with punctuation, oh my, madam, I'm Adam, with an exclamation mark and apostrophe would not be considered a palindrome in our code, even if it didn't have spaces. The capital letters, the exclamation mark, the apostrophe, all that is not captured correctly by our program. And so we'll deal with that this week. Here's one that has just capital letters and spaces, no apostrophes, no exclamation mark, but it's a famous palindrome. Able was I ere I saw Elba, was attributed to Napoleon, but it is not actually Napoleon who said it. And madam, I'm Adam with apostrophes, punctuation, that we'll deal with. So somebody mentioned last week that we could have this, we could make use of something called two-upper, but we looked at two-upper, and two-upper was takes a character and returns a character. It doesn't take in a string and return a string. And so we want to create some function that takes in a string and returns a string that's all capital. And to do this, we have to entertain and look at what really is a string. So what would the type for this function be? So if you enter in on the chat, what do you think the function would look like? Napoleon was dead before Idris Elba. Yes, that's a good one. Okay. Oh, yeah. Someone, Matthias said read maybe is not in Prelude. Yes, got to import the read. But still, the problem with good. Anybody know the signature of this all uppercase? All right, so I'll put the hint. All uppercase would be string to string. Okay, so Yes. So Roberto has an idea for all uppercase, taking in a function that translates A to B, and then takes in a second argument that's an array, a list of A's, and returns a list of B's. So yes, that is true, but we're gonna take a meandering way to get there. Where would we use it in our function is palindrome. So we have this is palindrome, where empty string is just nothing, or is nothing, and something is just whether it's the reverse input. So where would we use yes, so all uppercase does not exist. We would be creating all uppercase. Where would we use it though in the function? So we have this humane maybe, we have main, oops. Before the case statement, right? So we could do it there, except and so if we did it here, we'll take a look at some of the problems. Another place you might do it is here, around the X input that's coming in from getting line. So the problem with doing it here up at the top is we have the input, but this input is not related to this case input. So this case input has no impact on this input, nor on this input. So we'd have to surround both of these two inputs with the all uppercase. Instead, we'll just deal with it around the one place here in the get line. So yeah, dealing with the branching, we have to, we wouldn't actually have to deal with the branching itself, but we'd have to do it in two places on the input, because the way we're testing the reverse input to the input, if we only did if the cases would still be empty string or anything, but we wouldn't have the desire really to test anything that's capital or anything that's nothing. So we still want to leave it as something or nothing. And if we do it earlier in the where I have the arrow here, we don't have to worry that the case would not have capital letters. We'd only have to worry about it in that particular position. Okay, so but what are we missing? We're missing a $sign here between is palindrome and all uppercase X. So right here, if we did this, we might get an error that tries to apply all uppercase to is palindrome, and that would not be great, because the point is to apply all uppercase to X before it's interpreted by is palindrome. And so we have the $sign there, but now we have to take a look at how we do this in, let's say, English. Since we're working with English in this lecture, let's take a look at how we take a string, say it's handwritten, and how do we uppercase it? Well, we take the T, we take the A, we take the C, so we go left to right in English. We could actually do it either direction. It doesn't matter, because all we're doing is we're taking each individual letter and applying it. Yeah. So so in object-oriented programming, a map might do this. You might have a for loop with something counting the number of characters, obviously not in C++ or C, where we have no thing called length, as long if it's some array. And then we apply toUpper on the particular character, and we store it in some new array. So this works in object-oriented programming, but there are two problems. What is toUpper, and what's the other problem with trying to do this in Haskell? Anybody know? No loops. So here's maybe what toUpper might look like. We might have a character to character, an input character and an output character, and the input might match some character and output the capital version of that character. Yeah, I can't do counter. Well, you can increment things, but the point of doing maps is that you don't necessarily need them. And Haskell only deals with what you need, and we want to make sure that we can do it with only what we need. And so this toUpper, if we had to write this toUpper from scratch, how many case patterns would we have to match for the English alphabet? So how many letters are there in the English alphabet? 26, right? So if we do that, we'd think maybe there might be 26, but no, we still have to make sure that capital letters are transposed to their original capital letters. Yeah, we could use ASCII tables. We could add the addition. Yeah, we'll talk about what A and B are in a couple of minutes with the map. So instead of writing this toUpper case with 52 statements in it, we would avoid writing repetitive code. And one of the ways that we would do that is using modules. So, right, modules are really useful because what they are is someone has probably written most of the things that you need to use in order to do something that you might think is pretty repetitive, like changing things to upper. Yeah, great. But so let's take a look at Google Haskell.org, and you might search for toUpper, and it searched for it, and it says here character to character. And if we take a look at what it says, is it converts a letter to the corresponding uppercase letter if there is any. Any other character is returned unchanged. Okay, so this deals with probably using the value of the value of the ASCII table, right? Rather than doing a huge case statement, or maybe it takes the case statement of the ASCII value, and if it's below a certain value, it adds the value to transform the characters to the uppercase versions. Whatever it needs to, it does that. And so we don't have to worry about writing toUpper. We can just say, let's use the one that somebody else created. And so in order to use that, because of the, if we look up at the class, the type class that where this toUpper function exists, it's in the data.char class. And so in order to, module, I mean, and if we wanted to import that module, we would have to import data.char. This imports all of the functions and types from data.char, which if we look at it, if we look at data.char, there's a number of functions. And we don't really need all the functions, right? There's probably too many in there for what we need. And so usually what we like to do is specify what functions we really need out of that module. And so here we put in parentheses what we want out of it, and we say toUpper. And so now we might have this being our program. So many people have mentioned maps. So how do we do this without a for loop? Well, we deal with maps. And maps, you might have known maps from any programming language that has a map, like JavaScript, Java. Yeah, there's no Maven to import the full library. Yep, no. we're not dealing with, well, we're not dealing with projects yet. And so there is something like Maven. So we'll talk about that when we get to sort of packaging projects later. And so how do we handle the conditions in changing everything to uppercase? Happens in a couple of steps, and we have to take a look at patterns before we get into what the other steps are. How do we think about patterns? So patterns were simply sort of a map that we looked for a pattern, and when a pattern was matched, we did something to it, right? So we mapped the empty string to nothing, right? That pattern was the empty string. And then we did the catch-all whole to just whatever something it was. But what are some other patterns that you can think of? Anybody know other patterns? Two empty strings. So spaces. XXS. We'll talk about XXS or X and X's in a moment. But you might do other things. You might have a year and process that, matching that year to an age. The left is whatever the input pattern matching is, and the right is the output. And so if you're converting from a lowercase to uppercase, what would you do with an empty string? You probably still return an empty string, right? Can you use a variable on the left side? So yes, we will talk about using a variable on the left side. It's not exactly a variable, but sort of like the idea of destructuring in JavaScript. It's like calling something that is the input something. It's like making some value into an argument. There's also let, yes. So there are other things that we can do. But so what's a more general way to express the empty string pattern translates to an empty string? Yes, Robert has it. Yes. So empty square bracket returns empty square bracket. So empty square bracket is called the unit, but it's also the empty list, right? And so we know from experience that the quoted, double quoted empty string is just a list of chars. And if those chars are none, if there are no chars in there, then it's just the empty list, right? And so what are lists? Lists are groups of something with the same type, right? And they're usually like somebody mentioned X and X's, right? Head and whatever follows in tail. So this is usually the way we describe lists. There's some element and then there's a tail. Tail might be empty. There might not be anything in tail. You can have a single element in a list, or head and tail might be empty, right? So if we take a look at what a empty list is, or what the list square brackets are, it gives you a type star to star, gives you data, and if this type A exists, or if there's no value, so if there's no value inside of the list, we have an empty list. And if we have a value, then you have A colon some list of A's. Can you have an unbound list tail and then assign it later? So the empty list will take on whatever type of list, whatever type you add are going to be constructing with it. So generally the unit or the empty list is pretty flexible, and we'll take a look at that in a little bit. But really in Haskell, the way to write that head and tail is using that colon. So that colon is actually a function. It's a constructor of a list, and it is a pretty powerful thing, and you'll actually see it quite regularly in patterns, in creating structures that are important for understanding this map idea, and also filtering. And so really in Haskell, we would write head colon and then an array of tail. And that array of tail could be an empty list, but it would take on whatever type that head is. So if that head, yeah, we'll get to, so here's that information about colon. The colon is actually called the const constructor. And so what happens with colon is it goes between some type A and a list of that type. And so we generally talk in Haskell about a head and a tail, or sometimes people, as Roberto mentioned originally, I think, that head is sometimes called X and tail is sometimes called XS. And we'll talk about patterns for matching that list in a moment. But if we take the character like A as a head and attach it with the const constructor to the string BC, what do we get? Yeah, XS is out of Prolog, or actually XXS might be out of Lisp. also. So we see that. So yeah, we've got quote ABC, right? So we get quote ABC because that single character. So what is BC in that? Remember, it's an array of chars, and A is a char. So if we const A onto an array of chars, it just comes in as the first element of this new list. So remember that quote ABC is really just square bracket single quote A comma single quote B comma single quote C. If we did this, if we did one const the array 2, 3, what do we get? So we get the array 1, 2, 3, just like that array of ABC. So then if we take a look at the numbers 1 const 2 const array 3, so remember this is a single element array, what do you think we get? We get also 1, 2, 3. And we'll take a look at why in a second. But you just have to understand you can keep consting onto something that is an array. And what if we do 3 colon 4 colon empty list? What do you think we get? Right, 3 comma 4. And this is that empty list taking on the type of where A that's consting into it is a single integer or a single num, right? So 3 and 4 there are nums. We didn't give them a specific type. And so if we do this, we get an array of nums 3 and 4. So if we did that's interesting. I believe so. You'd have to do let var name equals 1. We'll talk about let and other things later. They have some interesting contexts, but we don't really need variables yet. We haven't. We'll talk about them more later, but we haven't needed them because the power of Haskell is in the fact that it sort of avoids having to deal with variables by, you know, lazy operations that can be evaluated later, right, when we need them. And so what do you think we get if we do array of 2 const with an array of 3? What do you think we get? So Roberto, oh wait, Matthias, type error. Why? Why do we get this type error?
Well, if you look at the, I'm not sure even if type error is the right word, but if you look at the function signature, right, you have an A, and then you have a list of A, and that, for lack of better terms, returns a list of A's, right? So an array 2 or an array with an element 2 or any array really would not match that type signature, the function signature. So that's why I expect it to error out.
Yep. So if we try it, we get an error, and it's the type constraint on num square bracket A. So num square bracket A would expect an array of arrays of type A, right? But the thing we're consting it onto is not an array of nums. It's just an array of nums, and so it'll have an error. And so I talked about a moment ago that the const is actually a function. You can actually put parentheses around it or after it, as if it was arguments to a function. And so you might get the single quote a const parenthesis bc, or 2, 3, or 1. And if you see here, we have nested parentheses, which is why you get the array 1, 2, 3 as opposed to 3, 2, 1, right? And here we have we're consting 4 onto the empty list, which makes a list with the number 4 in it. And the last one was an error, so we don't really worry about it. So now that we know how to construct a list, we can deconstruct a list, right? And map it. So map and reduce is a common action, popularized 2004 by the paper on MapReduce. This is just side information about Hadoop, right? Where everything is a map and reduce function, right? The reason for their value was in dealing with distributed systems. And so a lot of you are dealing with distributed systems in the idea of a blockchain. And one of the things that may exist in like Plutus and things like that is how we map through elements. And so Haskell is the underlying function, or something like Lisp that the Plutus looks like, and mapping is really important. So map and reduce, or at least the idea, the word map and reduce had been around longer than the MapReduce paper, but it was really popularized as really the structure of what you should really try to do with large data. We showed that loop in object-oriented programming a while ago, but how can we know about the construction of a list and the idea of pattern matching and iterate over a list without a loop? Anybody know the solution to this? Recursion. Yes, we might have this idea of recursion, and if you've never dealt with recursion, recursion is the idea of calling yourself. You might have some function which takes a number and outputs a number. And you might have this function take an x and then call itself, right? It's calling a function, but it's calling a function with x over 2. And what, yeah, okay, so Robert got it. What is this? What will happen with this function? Anybody know? So Robert got the right idea. Infinite recursion. We have infinite recursion. And what is infinite recursion? Bad. It's a feature. Okay. Yeah. No, not really, Matthias. Yes. Infinite recursion, usually bad. We want to stay away from it. And what is the way we keep something from experiencing infinite recursion? Define a base case, right? So there's a base case. So yeah, you could, well, even if you did that function in C++, that would go on forever, and your stack would overflow, and you would really not be happy. So yeah, base case, the word case sounds a lot like pattern matching. So CNC had this right idea. A base case means pattern matching, or guards, right? Guards are pattern matching, dealing with pattern matching. And so, whoops, if we're mapping over a list of chars, what is the base case? Yep, empty. So if we have this mapping function that maps some array of A onto some array of B, and we input a list, right? Says Mario, and we take the case of that list, we would have this base case where we have the empty list becomes an empty list, right? So we saw that before. An empty list becomes an empty list because there's nothing you can do. So the empty list of B is similar to the empty list of A in that it can take on whatever is being const onto it. So what are the other cases? What's not an empty list? So we might have this head and tail, right? And we might do something, right? So this head and tail, or X colon X's, you might do something, right? So what are the things you could do? You could use recursion. You can use recursion to do something. And what we always want to do with recursion is get closer to the base case. So how do you get closer to the empty list? If you have a list of something, how do you get closer to the empty list? Remove the head. Yeah, you either remove it or you do something to it, and then you recurse on just the tail. And so you do this const here. You do something with the head, and then you recurse on the tail. So this tail is obviously shorter than it was with the head, and so you're getting closer to an empty list, right? So let's rename or rewrite this mapping function name with all uppercase, and give those A and B types the char types we're expecting, and just rename that const. We're going to capitalize the head, and we're going to uppercase the rest of the tail, right? So what is head in this condition here, in this case? It's not an empty list. Head is like A, yeah, so X. What is X? The first char. Roberto got it. First item in the list, because how you define a list was A const square bracket type A, right? So the A const onto there is type A, and here we have, we're consting onto an array of chars, so we have a char colon an array of chars, and so we're going to uppercase the tail. If we gave all uppercase the empty list, what would happen in this all uppercase function? We would just get the base case, right? We get the base case, we would return an empty list. If not, we would have to capitalize head. And how do we capitalize the head? We've talked about it a number of times, right? We use to upper. And so the to upper here said, all right, so we're going to take the first character of the head, and then we're going to uppercase the tail. And what happens in the second iteration or second recursion, the depth 2 of this recursion pattern? Say we had the string ABC, lowercase abc. in the first recursion, we get A colon the empty string BC, and we do 2 upper on A. So we would get capital letter A, and then colon all uppercase quote BC. And so what then happens to the all uppercase BC? It comes in, and the 2 upper head is still in memory. It's still on the stack of things. It operates on the rest of the list until we get down to the empty string. All right, so now all together, we have this 2 upper imported. We have is palindrome that didn't change. We have humane maybe, where we output the string of what happens. And then we get all uppercase, which has the 2 upper of the head and the uppercase of all uppercase of the tail. And we just apply that to X before we apply that uppercase string to is palindrome. Can you use list syntax in the input variable in a function? No, I don't. Well, So the parentheses here are just saying that it is an item. It's not saying it's a list, but I think there is another way to represent it, but I wouldn't say that you could use the square brackets, and it's never done in Haskell. So you would always see this parenthesis head colon tail as one item in the case list, or one argument. So all uppercase is kind of specific. Okay, so maybe I gave too much away in that next slide. How would we generalize it? So we would generalize it by maybe calling it mapping function again, taking some f, whatever f is, and applying A to A, right? And so, all right. So remember, Robert, you can't do the array const an array when the items in the right side, in what you're consting it onto, is an array of integers or nums, and not an array of arrays. So if you did square bracket 1 comma 2 const square bracket 3 comma 4 inside of a second set of square brackets, so double bracket, yeah, you can we'll do mapend and things like that, but const is different than mapend. We'll talk about those things later. But what we're doing here, so how would we make the mapping function do the task of all uppercase? Here in the mapping function, the function to apply then would be to upper. So we would call mapping function to upper of ABC. And so if we get some information about this map function, then we notice, somebody mentioned it before, that if you have an A and a B, and you have some function that translates A's to B's, then you can use this map function and apply some function where A translates to B. Can A and B be the same type? Yes, they can be the same type. So if you have A that translates to A, it falls in the same category as A translating to B, but B is the same type as A. So it doesn't matter what the A type and the B type are, as long as you translate from one to the other. If they're the same type, it's totally fine. So I'm going to take a look. We have this. Let me make this bigger. Oops. We have the function for is palindrome here, and so instead of all uppercase here, if we did it directly with map, how would this look? We would do here map, right? And then what would we add to map? To upper. And then we don't need that whole function. We can use the map in there. So if we open that file in GHCI, and we did main, and we did TacoCat without capitals, we would get, yes, that's a palindrome. And if we did TacoCat with a capital T only at the beginning, we'd also get, yes, that's a palindrome. Okay. Let's take a look here. Okay, so here. So now we're going to practice. Does map spread to all CPU available? Haskell does parallelize things, but Haskell without some specifications doesn't really adapt to multi-CPU without the sort of configuration that's necessary. So just like C++, you have to sort of add some features that allow the map to use all the processes. And the nice thing about that map and our mapping function is they're pure. And pure functions are really powerful because they can be parallelized. You can apply one before the other as long as it has an intermediary. It knows how to get the value. It can operate on whichever one comes first, but recursion, unfortunately, has a sort of stack process where the operations sort of have to be evaluated in order from the last to the first. However, the nice thing about the way that something can be evaluated in, say, a map is that you can use the option to take a certain number of elements to be mapped. And so if you wanted to process just a certain number of elements, then you could take those elements and only operate on some of them. Anyway, so we're going to practice transforming some text. So we're going to write a function that takes a list of floating point numbers. So the numbers of cups of coffee we say we drink. So say Matthias says he drinks 1.9 cups or 10 cups, depending on the day, right? But say I say, or 42 cups, he says, and I drink 2 cups. Some people say we should multiply that number by 1.5 because the cup of coffee should only be 6 to 8 ounces. And nobody really knows what an ounce is. Nobody really measures anyway. So do we drink 1 cup or do we drink 3 cups or something like that? So we want to write a function that takes a list of yes, I miss milliliters. Yes, so we take a list of A elements. Here you might think floats, maybe. So you might put a constraint on that A type. And then we have this function definition, which takes in an input array of cups and then does something using recursion. So I'm going to split you guys into groups, and you're going to, whoever is in your group, you're going to ask how many cups they have, and that's going to be the input list. And we're just going to, we're not going to work on reading in arrays. We're just going to do it on GHCI as an input array. And I'll show you how to do that once you write the function to handle this. So let me break you into groups. I'm going to take a screenshot of this. And I'm going to put it on the Discord and here, so you can have it to reference while you're writing the program. Okay. You should all be able to access that file. I'm going to put it on Discord as well. Okay, so let me split you up. Okay. So you should enter your rooms.
Hi, Eli.
Hello.
Sorry, I had to restart my Zoom so I could share my screen.
Okay,
I got kicked out of my room.
let me see.
I was with Matthias and
And Bumsu, yeah. Assigned to room 1. Okay.
thank you.
And num constraint.
It's probably a fractional that I would use.
A float? Oh,
Yeah, so the fractional constraint on A would work, for example.
sorry. What's a fractional? Is it
So num is also applies to integers, for example, but you cannot be sure that if you multiply a integer with 1.5 that you'll also get an integer out. So that is well, there's a different constraint as well, which is a fractional constraint. You can actually test that out just by writing the function as you want it to. And then once you try to import it in GHCI, you'll get an error message on that constraint, because that's what happened to me. I was like, oh, of course, right? It cannot just be any A's. It cannot be any nums, probably. So
is it like this? Fractional.
Yep.
Yeah.
Yep.
You do colon I fractional if you want to.
Oh, it's I.
Mm-hmm.
Wait, I forget. What's the difference between, why can't we get, because it's not a type, it doesn't have a type, that's why I can't do.
So colon T is about a particular type that is instantiated into the memory of the GHCI. So colon T is the type info about something, whereas I is about the information about a type or module or something like that.
Okay. Let me do. So,
if you did let I equals 3 : fractional, and then you did colon T I, you would get the information about that that fractional item.
yeah, I get what you mean.
Yeah.
Very good. That looks good.
Yeah, I think so. So fractional A, constraint of A, gets a list of A's and returns a list of A's. So works where we're working with strings, and the other one would be
head tail format, right?
Yeah, of course. Should we do just head tail? We can do just this is
XXS or head tail.
right?
Both.
Yeah.
It is, yeah.
I would do X and XS because head and tail are also functions.
That's right. That's true. I didn't think about that. Okay, so would be, what are we doing? We're doing
So essentially the purpose here is to multiply every single element in the list.
Hello. Ooh, good. You got fractional. Fractional is excellent.
Cool. Okay. And
so are you going to be doing sort of the so if you do this without the case statements, you're doing it correctly, right? So what are the conditions that you want? Yes, you have empty square bracket and ends, right? And that looks good. Looks good. So how would you define a main to take that value?
Like a main to run this this method.
Yeah.
I mean, we could do a couple of things. I mean, we could do like not like a listen, but like an event handler list for like a get line or read from like an input. I guess if you want to use console. I was thinking of making like a I guess a variable inside
Yeah,
main? You could
that
hard
works.
code it. Okay.
Yeah, you can hard code it. You can do
Okay.
either. You can do either way. Do either way.
Okay. Would do notation be acceptable at this
You
point?
could, yeah,
Okay.
you can use do. We prefer do because it's just less
Okay.
less characters.
I'll try to copy over as much of this to 3.5, 4.2. Oh man, it's been a minute since I've done something like this. Okay, and then next one will just be cups to real cups, and we'll pass in cup. And do I need to return? I don't need n, do I? Oh.
No, you don't need
Oh boy, this shows you how dated my
so
experience.
if you wanted to, so you wouldn't return anything from main, but
Right.
you might print something
yes.
in main, or you might put stir line or whatever. The problem with cups to real cups is it is not a string. So how do you represent something as a string?
I would
Print.
You
it
could
a
use
show.
print. Yeah,
Oh,
you would give it a show. So you could also do print. Print automatically gives it a
Okay.
show.
mhm.
So print is the same thing as put stir line with the show, right? So yeah. Excellent. So now try that. Try that in GHCI. I'm going to go to another group, but you seem like you've got it.
Let's see. Okay. Here we go. Got
How are you guys doing? Okay. Hey, you muted, Narendra.
Yeah, not good, Ali. Like
Okay. Let's
we
take.
couldn't able to hear each other. The
Oh.
main problem, yeah, and we are doing it with our own local PC, so we couldn't able to share it right away.
Okay. So can you share your screen, Narendra, to show me what you're trying to do? Or
Yeah,
no?
no, Ali, I'm in a iPad, but I'm doing it in with my local PC.
Okay.
So,
All right. So
yeah.
I'll share. Let me just see.
Yeah.
I'll share what, and I'll work on it with you. Share screen. Can you guys see my screen?
Yeah.
Okay. So there are a couple of ways to do this. So so cups to real cups, right? We have a type, some constraint, and then we have an array of A's, and we want to return basically the same type. So we had like 1.5, we probably want to return 3.25, right, or something. And one type that works for this is float A, so that works as one type, but an even more or less restrictive type is fractional. And so fractional just means you can do multiplication and division on it. And so if we want to define cups to real cups, we would have some input list, right? And then we want to do something with this. So we would do case input list of, and so there are two ways to do this. You could do case input list of, or you could do this. This is sometimes easier. So you can just write the function. So input real cups. When it has an empty list, it just returns an empty list. And when it has something that's not an empty list, so you might have X and X's, or head and tail, or whatever. I like X and X's. Then you might do something to X, and then we do recursion copes to real of XS. Okay, so what do we do to X to get the 1.5 times the value in a list? We just multiply X times 1.5. And this says X times 1.5, and add that onto a list of whatever we do with the tail. So if the tail is an empty list, we just return the empty list. And if it's another value, then we take the head and we multiply it by 1. And so if we have a main function, we would do cups to real cups of, let's say, 1, 2, 3, or something like that. What do you think we would get on the output of this? So say we print out this, this return. What do you think we get? So here it's saying something that I can't even see. Use map. Okay, so yes, we should use map, but we're not going to use map. We're writing a specific function. So we'll see what it does. Okay, so let's quit. That's all we're going to do in this function. So if we do GHCI and we load cups, and we do main, what do you think we get out from the main?
We'll get 1.5, 3, and 4.5.
Okay. Yep, exactly. So does that make sense, that what we did there?
Yeah.
Okay.
Can
All right,
you hear
I'm
me?
gonna go. Well, yeah, I can hear you now.
Okay. So
All right. So it's a pretty simple function, right? Well, we could write the whole thing using map. And what we would do is you would do map times 1.5. And that's actually a function. And we would do this on 1, 2, 3. So this is the same result as our function. Make sense?
Yeah.
yes.
Okay.
Yes.
All right. I'm going to go check on another group. I'll be right back.
Thanks, Ali.
Thank you.
How are you doing?
Fine, fine. We are trying to replace some functions
Okay.
we're trying to adapt the previous function with this new purpose.
Okay. Any problems so far? Or
No, we are in the
okay.
we are in the exercise.
Okay.
of-
Okay. And the short solution is we could do this with map. We don't need this annoying function cups to no cups, right? We can just do it like this. we can do map. Oh wait, I'm not sharing. We could just do map and then the function multiply by 1.5, and then we can have an argument that is a list of 1, 2, 3, and this would be the same as the function we just wrote, right? So there are easier ways to do it, but I just want you familiar with how to process through something like this. So we'll get to a reason why it's actually valuable to be able to process a list in just a moment. I think I'm going to pull everybody back in, and I will, yeah, I think.
Great.
Like it's doing, what it looks like it's doing, that show actual cups, right? You have your X there, but the function is not complete here, right? You also call cups to real cups, so you have the recursive call in XS, but you probably want something else. But since everyone seems to be here, I let Eli take over again.
Yep. So.
Yeah, my code was so bad, Matthias ran away.
No, do you want to continue with what you were saying about the function there?
Sure, I'll
so
be
that-
your guinea pig.
Okay.
The text is super small, so.
Oh, how do I make the text bigger in K? Oh, easy. Okay, that's real easy.
All right.
Or everyone just get a 32
Yeah, I'm
inch
sorry,
screen.
guys. I don't know how to do that in console, though.
Okay. So you can do this, except what is happening?
Is it the empty set?
Yeah. So why would we have an empty list returning 0? Why would we want 0?
I ran out of ideas.
Okay, so the base case can be anything. It can be anything, but what you're trying to do is you're trying to return a list of floats, right? Your return value is a list of floats, and so the return of, or the result of the pattern matching should always be a list of floats, because what you want to do is you want to chain on, you want to keep connecting lists of floats. You could do 0, but that would mean that one of the elements was actually 0. And really, you can chain onto a list of floats that has an empty list. So the empty list is, in fact, a list of floats. It's just a list of no floats, right? And so that base condition is correct. You have nothing happening. You have a new list of floats that returns when you have no floats left to process. And your pattern for the next one is correct, right? The X and X's is correct. And then you have their show actual cups, which is a function, right? And what does that function do? It just returns num cups times 1.5, right? Then you have cups to real cups, which would be the recursive step. But what do we, so say you're on square bracket 3. Say you have this as your cups to real cups input. So if you have square bracket 3, it it goes into the second case statement, right? Because square bracket 3 is the same thing as 3 : empty square brackets. And then it says show actual cups of 3, and then cups to real cups of empty square bracket. But it's not combining those two values. It's just doing those two functions. So you're not actually combining the result of show actual cups of 3 and cups to real cups of the empty list. We would expect the result of show actual cups, so say it was 3, to be 4.5, right? Or yeah, and cups to real cups to be the empty list, because the empty list input there to cups to real cups is the empty list. But what we really want to do between show actual cups, this 4.5 value, and the recursive call that returns an empty list, is we want to const them. We want to connect them. And the way we connect them is with the colon. And I'm not sure if having a new line will break. Oh, it's not a new line, it's just wrapping. Okay, that's good. All right, so now if you try to load this, what does it say? Hey, module loaded, right? So now try cups to real cups, right? So that should be, if somebody says they drink 3 cups and if the output is, yep, good way to test, excellent way to test. Look good? Robert, does that make sense? Or not really?
Oh, sorry, I have a secondary mute button. No, that's perfect. Just out of curiosity though, when you have a case statement on the right-hand side, can you just put one line after the other like I had it before? Suppose we weren't doing the constant, just had statement 1, statement 2. Is that legal, or do you have to have a break line, or you know what I'm talking about?
So you can do a statement that has sort of multiple lines, but it's really not
Frowned upon?
not advised, because what
No
case
data
statements
constructor.
are, is not for complex evaluations, right? They're sort of they're for simple evaluations. And the reason we use the case statement, or the reason we just overload the cups to real cups, depending how you did it, is a way of writing simple statements to do something. If you really are doing multiple statements, you may want to overload the function and have a do block with, you know, multiple statements that do things. What you also may want is the bind. So binding the output of one thing to the next thing, that's another thing you can do. But really, Eli will not hurt you ever. Eli will never hurt you. Eli will not come after you if you do something wrong. Don't worry about that. Yeah, so if Matthias mentioned, if you want comments, put 2 dashes. So, yeah, same thing for the case statement. I think you wanna comment that out. But if you really want to comment the whole block, you would do a left curly bracket and a dash, and then all the way at the end you do dash and right curly bracket. So that's gonna comment out that whole block. All right, sound good?
Oh, I forgot you're recording this.
Oh, don't, it's great. It's perfect. We can edit out stuff later if you really don't want to show that. But
No, it's not that. It's just I'm putting this fear out into the world that Eli will hurt you if you don't.
no. I will not hurt you. Okay. So I'm gonna share.
You want me to stop sharing?
Yeah. All right. So now, so now we've done this this task for transforming cups to real cups. You can actually do this whole, so this function is pretty moot, because you can actually just do the map function, and you could do map multiply by 1.5, which is actually a function, and you can apply it to this list of numbers, and it comes out with the right value. So this is much simpler, and this is the power of map, in that you can pass it in a function and have it apply that to some list. Now, the idea is great that you could do that, but it has some limitations in that we can't really do this map and remove some characters. Remember, we wanted to remove spaces and exclamation marks or whatever, commas, in the phrases that we're giving it. And so we may want to, similarly to this mapping function, create some function that filters spaces out. And so filter is sort of a analog of removing things from a list, from a string, from whatever you're working on that's an array of characters or numbers or whatever. And so we have basically the same thing, but we have this missing section in the middle, right? And so what do we put in for this particular condition here? Let's see. Oh, what is the difference between, so the missing condition is here. What do we do here? Before we get to process the head and tail, and in fact, in filtering, you're not actually changing the head. You're either doing what? Putting the head back on the tail. So what is the other thing that you'd be doing if you didn't want the head there? You'd be removing it, right? And so we might do, if we're filtering spaces, this condition of where we have an empty list, which is great. You can't remove anything from an empty list, so we return the empty list. And if we have the condition where the head is a space and the tail is something, then we do the recursion, but we don't attach the head back to the tail. We just want the tail if the space is there, because we don't want the space. So we just recurse on the tail. And then if the head is not a space, we get the next condition, right? Which is head colon tail. And so then we take the head and add it on to whatever the recursive call. Yeah, so I'm just using these words, head and tail, for explicit description. We use X and X's in real coding, but you can use anything. You can use head and tail, but if you ever wanted to use the head function inside of the operation that you're doing on the right-hand side, then you would really need to call this something different than head and tail. Okay, so so most people prefer XS. In anything in the future, we'll be dealing with X and X's. Anyway, but just for this first demonstration of what filtering is. So Robert had a question of what's the difference between, let's go, between this multiplication on the left of the 1.5 and multiplication on the right of 1.5. So nothing in multiplication. But if we get some information about what the star operation is, you'll see that it has this thing called infix L7. Having the operation on the left side means that when you're applying something, it means it can be on the left or right, but it has a certain precedence to operate on the left or right. Whereas if you do division, we get infix L7. But if we try this, it works. But if you try, oh, actually, I thought it did work. Didn't work. Okay, so they both have the same infix L precedence, and so the operation is interesting in that they don't produce the same result. The thing about multiplicative precedent or multiplicative precedence is that it allows the left and right hand side to be switched, right? So the order of multiplication doesn't matter, but it does matter with division. So if you take the map of divided by 1.5, it says 1 divided by 1.5, 2 divided by 1.5, 3 divided by 1.5. But if you do 1.5 divided by, this goes through the array, the list, and says 1.5 divided by 1, 1.5 divided by 2, and 1.5 divided by 3. So the map takes the precedence of whatever is first in the left. The infix L takes the left-hand operand first or second. So yeah, Matthias has the statement of what happens when you apply this to a 1 divided by, which is actually a shorthand, right? Where this this type of parenthesis here is actually a simplification of this function, whereas the 1.5 divided by is a simplification of this expression. These are called lambda functions. We'll talk about them later. Oops.
We forgot the arrow.
I forgot the arrow. There. So this is a simplification. So this is just shorthand. That multiplier is the same. So if we did x, this, so this, this function is the same because of the multiplicative identity, right? And the associativeness of multiplication. We have either way being the same value for multiplication. Anyway, okay, so now back to filtering. So if we have the space and the tail, we filter out the space by just not adding it back to the head. And if we have a head that's not the space, we add it to the head again. So the resulting recursion will have that head back in the top spot. So now we want to do some filtering function generically. So if we have this filtering function where we have a head and a tail, and we want to do something with that head and tail. What's going on with my slides? Did I delete the slide? Anyway, okay, so we'll go do it in code. So if we have a generic filtering function, right? And we want to apply this filtering to some list, right? And so we're applying it with some function that goes from A to B again, and we take in some list of A and output some list of B, right? Where A and B can be the same thing. Let's say we're restricting this thing to filtering chars. We can add a set of constraints, right? Where we could say A is char and B is char, or something like that. We can do that. So what A and B here is a function. So the parentheses just identify that A is transitioning to B in arguments of some function where A returns B's, and then the next argument is, so this first argument is a function, second argument is a list of A's, and the output is a list of B's. So if we're requiring A's and B's to be the same, we can just make this simpler. But this is less generic, right? Even though we're restricting it to chars, this is less generic than the other way. anyway, so if we wanted to write filtering errors, we're going to use the overloading here. So let's say some not space function. So this says maybe instead of A to B, what we want here is not A to B, right? So what we really want is a Boolean. And the way we do that is we could have this. We could have the Boolean be, but we're gonna say A is a char and B is a bool. We'll do that. We could have this not space function, which takes an A and returns whether or not that character should be accepted. We could then write some list of empty characters, and for that condition, we would have the empty list. So if we have to define what is not space would have the function signature A to bool. And so we would say here, this function has signature A to bool, and we're having a restriction here on A where A is a character. And so how do we write this not space function? Yeah, changed it. So what would this not space function look like? So it would have an input character. And what would we do with this input character? Yes, Matthias.
Yeah, one naive first approach would be just to check. So with you, in your style, you would use a case again, right? And you would check if input char is the space character. And of course, there's many different space characters, right?
Yeah.
But
So
let's go with that. And
so if it's the space character, we would do false. And if it isn't, anything else would be true, right? So yeah, so this is so filtering. Yep. So if not equal empty space, that is one way to do it. Or don't try the mapend on this yet. And so in the condition here that not space, we don't operate at all on this function here on the empty list, but say filtering chars not space. What do we do if the condition is X and X is? Yeah, you could rewrite this, not space, can't type. False or not space. This is the overloaded way. Anything else? This is another way to write that same condition.
Guards.
Yeah, you could also use guards. But guards are really for more conditions or lots of conditions. They're pretty useful in lots of conditions where you just create a line down that is all the cases that would be pattern matched. Basically, the guard is or is this matching? So here we have, what is the condition? What do we do if for this condition? Anybody know? Okay. So we are operating on X and X's. So we might do something like an if then else. So if not space, right? And what do we input to not space? We input X because that's the head that we're worrying about. Then what would we do? What would we return, or what would we give the value for not space? If it's not a space, then what do we do? X. Okay, so Robert ran out of coffee, so that's what we always have to do. Else, what do we do if it is a space? Oh yeah, sorry. Filtering. Yeah. If X is a space, this else condition, if it is a space, then we just do filtering chars excess on the tail, right? So we are using an if then else to handle the condition. So if we take a look at this, redundant bracket. Yeah, you don't need the parentheses here, and you don't need them up here. But okay. Yes, so we really wouldn't do this in real life. We would use the filter function, and we would say not equal empty space. But for the purpose of this filtering chars, okay, we would have this. Wait. I'll figure this out. Okay. Oh, oops, I forgot. Filtering chars, not space. And this is redundant. Anyway, okay, so if we have this, and we do we load filtering. Oops.
You need your type constraint again.
Yeah. I didn't like that type constraint. What am I missing?
You can remove that one, that type constraint there, and it should work. Or maybe not.
Yeah. What am I missing? I'm missing something.
Can you do a split screen?
Yeah. Actually, I'm not using Tmux. I should be using Tmux.
Is character the lowest type? But maybe you have to just manually make everything, all the A's character.
Sweet. Let's leave out the
It looked like you had Nick shell running. The
yeah.
loading time.
This for a second. So if we load that, and we do filtering pairs of Taco cat, what do we expect we'll get? Oh,
Double quotes.
yeah. We're getting the error. Didn't match error to pool actual error. Oh, filtering pairs. Not. We get Taco Cat. So now the question is, how do we, so we're over time, how do we apply this filtering pairs to our palindrome situation? That's going to be the homework. So the homework is taking the filtering pairs and the capitalization. So we can use the map to upper X or whatever the input is, and we can actually use filter. So not equals space on Taco Cat and do the exact same.
It's a forward slash.
If we do the filter not equals empty space Taco Cat, we get the same thing as our function that we created. So this filter, if we do information about, I think it's I, but it might be T. Yeah. This says it's a function, it's shorthand for a function, right? Where we do x not equal empty string, right? So it's a function that takes a char and returns a bool, and filter is a function that takes takes something and returns a bool, and then applies this to some array of, or some list of A, and returns a new list of A. So that is already defined in Prelude and GHC. that these are options that are available to you. So if you did for the homework, let me see what happened to my slides. Let me edit it. So the homework. I thought this was the right version. So homework. Apply. Filter. Not equal space to some array of characters and apply to map to upper to some array of characters to produce the palindrome, the palindrome with without that accepts spaces, that ignores spaces and different capitalization. So that's the homework. I wanted to get to what happens with filtering out punctuation. That's going to be the beginning of next lecture. Okay. So any questions so far? So I'm going to CNC, did you have a question? No? All right. See everyone next week.
Thank you, everyone.